This video is about distance time and displacement time graphs. We will discuss distance time and displacement time graphs and talk about how to find the average speed and the instantaneous speed on distance time graphs. Let's begin with distance time graphs. Here is an example of such a graph. On these graphs, distance is on the vertical and time is on the horizontal axis. The letter symbol for distance is S, and the letter symbol for time is T. Here, distance is given in meters and time is given in seconds. The units that you will most often see for distance are meters and kilometers, and for time, seconds, minutes, or hours. You might also see some other units for these quantities, for example millimeters, centimeters, or milliseconds for time, although you will mostly see smaller units like these when you learn about waves. When you are looking at a distance time graph, or in fact any motion graph, just remember that the graph tells a real-life story. Let's see a possible story for this graph. We will discuss what could have happened during these four segments of the graph. Let's assume that this graph shows the journey of a rabbit from her house to her friend's house. The rabbit is at home at the 0, point or origin of the graph. The first segment tells us that the rabbit traveled 1000 meters in 500 seconds. Here, the rabbit walked from her home to the bus stop. The second segment is horizontal, which means that the rabbit did not cover any distance during this time, which means that she was probably waiting for the bus to arrive. The third segment is much steeper than the first segment. In fact, the rabbit covered twice as much distance in half the time. In other words, she was going much faster than when walking. So we can assume that she was taking the bus. The final segment is less steep than the previous one. So the rabbit here was again traveling slower, probably walking from the bus stop to her friend's house. We mentioned the steepness of the line segments in our story. Another way to say steepness is gradient or slope. Often in physics, the gradient of a graph represents a real-life quantity. Let's see what the gradient represents here. Gradient is the change in the variable on the vertical axis divided by the change in the variable on the horizontal axis. In math, you probably learned change in y over change in x. Here, the variable on the vertical axis is distance, and on the horizontal axis is time. So the gradient is equal to change in distance over change in time. Change in distance over change in time is equal to speed, so the gradient on a distance-time graph represents speed. Let's ask and answer a few questions about this graph. In the first question, we have to find the distance traveled by the rabbit while she was walking to the bus stop. It is represented by this segment. We can see the distance traveled on the vertical axis, which is 1000 meters. For question 2, this is the segment where the rabbit was waiting for the bus. Let's read the time from the horizontal axis. This gives us 500 seconds. As we mentioned during our story, the faster the rabbit travels, the steeper the gradient will be. This is the steepest section of the graph, so the fastest part of the journey is when the rabbit is traveling by bus. Let's calculate the speed here. I will denote speed by v, and this is equal to change in distance over change in time. The change in distance during this section is 2000 meters, and the change in time is 250 seconds. So we have to divide here by 250, which gives us 8 meters per second for the speed. One final note here. Even though on exam questions, you will often see graphs with straight lines, this is not how actual real-life motion graphs look like. Real-life motion graphs would be curvy because motion is continuous and there are no sudden instant changes, as for example here when the rabbit arrives to the bus stop and her speed dropped to 0 instantaneously. Next, let's discuss displacement time graphs. Here, instead of starting with a graph and creating a story, we are going to start with a story and create a graph. Here is the story. And here is the grid where we will draw the graph. One of the first things that you probably notice is that the displacement has negative values. This might seem strange at first, but remember that displacement is a vector, so it has a direction. On a displacement time graph, we are not only able to see the distance traveled by the object, but we can also deduce whether the object is traveling in a positive or negative direction. Which direction is positive and which is negative is arbitrary and depends on the question. Here, since town X is our starting point, we will take its displacement to be 0, and we will assume that town Y is in the positive and town Z is in the negative direction. Note that the assumption on a displacement time graph is that the object is moving in a straight line, so it either moves in the positive or the negative direction. Let's start drawing our graph. The car starts from town X and takes 1 hour to drive 50 kilometers. We said that in this question town Y would be in the positive direction, so the graph here looks like this. The driver spends 30 minutes in town Y, so there's no change in displacement, and the graph looks like this. Then the driver turns around and drives back to town X, so now he's going in the opposite direction and takes 45 minutes to arrive back in town X. Then again he stays stationary for an hour, so the graph is horizontal. Then he drives to town Z, which is 100 kilometers away from town X, but in the negative direction, so here the graph looks like this. He spends a short time, so 15 minutes, in town Z, so the graph again is horizontal, and then in 3 hours he arrives back in town X. Let's ask and answer some questions about this graph. The magnitude of the displacement is the distance between the start and the end point of the car's journey. Since the car starts and finishes its journey in town X, its displacement is 0. To find the distance traveled, we have to add up the different distances that the car traveled between the towns. By reading the text or by looking at the graph, we get 50 plus 50 plus 100 plus 100. This is equal to 300 kilometers. For the second question, recall that velocity is displacement over time. Since displacement is 0, velocity will also be 0. Speed is distance over time. The total distance traveled is 300 kilometers, and this is divided by 8.5 hours, which we can read from the graph. This is equal to approximately 35 kilometers per hour. So this is the average speed of the car for the entire journey. Finally, let's see how to find the average speed and the instantaneous speed on curved distance-time graphs. So far, we only worked with graphs that had straight line segments. However, we mentioned that in actual real-life situations, these graphs are almost never straight, but curved. Let's see how to work with such a graph. This graph shows how the distance traveled by a car varies with time. Let's ask and answer some questions about this graph. In the first question, we are looking for the average speed of the car during the first 6 seconds of its motion. In other words, we are trying to find the average speed between this point and this point. We have seen that the gradient of a distance-time graph gives us the speed. So to find the average speed between these 2 points, we have to find the gradient of the line connecting them. The gradient here is change in distance over change in time. This is the change in distance, and this is the change in time. The change in distance is about 36 meters, and the change in time is 6 seconds. So the average speed is 36 meters over 6 seconds, which is 6 meters per second. In the second question, we are looking for the instantaneous speed at t equals 6 seconds, so at this point. Remember that instantaneous speed is basically the speedometer reading at a given moment. We have learned that speed on a distance-time graph is given by the gradient, but here we only have one point, so the question is, how can we draw a line to calculate its gradient? The answer is that instead of connecting 2 points to get a line, we will draw the tangent at this point. The tangent is the line that touches the curve at this point and looks like this. The instantaneous speed at t equals 6 seconds is the gradient of this tangent line. To find the gradient, we can pick any 2 points on the line, and since on some questions it is expected that you pick points that are relatively far away from each other, here I will pick this point and this point. These are also good points to pick because they are at the intersection of major grid lines, so the horizontal and the vertical distance between them will give us whole numbers. So the vertical distance between the points is this, and the horizontal distance is this. So for the distance we have 60 meters, and for the time 5 seconds. Therefore the instantaneous speed is 60 meters over 5 seconds, which is 12 meters per second. Let's see a few important concepts that we learned through this discussion. We saw that to find the average speed on a distance-time graph between 2 moments in time, we have to find the gradient of the line connecting the 2 points that represent these 2 moments. We learned that to find the instantaneous speed on a distance-time graph at a given moment, we have to find the gradient of the tangent to the graph at the point that represents this moment. And we mentioned something that you probably already know from math, which is that the tangent is a line touching a curve at a point. Let's summarize what we have learned in this video. We have seen that the gradient of a distance-time graph, and in fact of a displacement-time graph as well, represents speed. We mentioned that displacement-time graphs can have positive and negative displacement values. We discussed that on a displacement-time graph, the positive direction represents motion in one direction and the negative direction represents motion in the opposite direction. We have added that these directions are chosen arbitrarily. Through 2 examples, we saw that average speed on a distance-time graph is represented by the gradient between 2 points, and that instantaneous speed on a distance-time graph is represented by the gradient of the tangent. And we briefly mentioned something that you probably know from math, and this is that the tangent is a line that touches a curve at a point. This completes our discussion about distance-time and displacement-time graphs.